Okay, so in this video, we're going to talk about the addition rule. And to talk about the addition rule, we need to introduce the concept of mutually exclusive events. So two events, E and F, are going to be called mutually exclusive if they cannot occur at the same time. So in terms of Venn diagrams, that means that the circles are not going to overlap, right? So I have used a little bit of Venn diagrams in my couple examples before. For those of you who have never seen or don't understand what this is, it's pretty simple. It's a way to represent sets and their who belongs to a set are enclosed in a circle. So, for example, if I roll a die and I get 6 numbers, those are my possible outcomes. That's a 3. Then you put probably this circle, just to say that's my universe, everybody in there. And if I want to say, well, the set A is the event that are landed on an even number. So this is a circle that represents that even number, right? Anything in my red circle is event it belongs to the set A, and or event A. And if I say my event B is landed on 4 or above, so this would be 4, 5, or 6. Sorry, I should have used a different color, so let me pick a different color for that one. So 4 or above, those would be it, right? So those two events, for example, are not mutually exclusive because they overlap on the 4 and the 6. Okay, so yeah, so two A and B will be mutually exclusive if the circles don't overlap, and if they do overlap, then this is the, I also used that term before, this is the intersection, the overlap, okay? So this is what is called A intersection B is this part where they overlap. So those are the members there are those that belong to both A and B. So very simple examples are the following events mutually exclusive. So A, you roll a 3 on a die, and 4, you roll a 4 on a die. Those would be like my example, but my circles would have a circle would only contain the 3, the other one would only contain the 4. So yes, they're mutually exclusive, right? Next example, I randomly select a male student from a classroom, and B, the selected person was a science major. So I'm assuming maybe the context is I select a person at random from a classroom. A is the event, the person selected is a male student. B, the event, the person selected is a science major. Are they mutually exclusive? I guess not. They could be males who are science majors, right? So that would make them not mutually exclusive because they would be somebody in the intersection, right, in that overlap. My third example is from a deck of cards. So this is saying if you're familiar with a standard deck of cards, is the most useful, more common to talk about it in the U.S. So we have 4 suits, spades, clubs, diamonds, and hearts, and every suit goes from ace, and then 2, 3, 4, 5, up to 10, and then to face cards, so the jack, queen, and king. So there is 1 ace of each suit. There is 1 of each for each suit. So there's a 10 of each suit. So if I selected a ace from the deck of cards, and then my second event is you select a heart from the deck of cards. Are these mutually exclusive? They are not, because there's going to be at least exactly 1 card, the ace of hearts, right? So it could happen, both could happen at the same time, that I gave you a card that's both an ace and a heart. So they're not mutually exclusive. So very simple examples. So now we want to talk about the addition rule. And this was just a setup to talk about this because this is the language we need. But the addition rule is for when we want to find the probability of an OR of 2 events happening. Either the event A or the event B happened. In the multiplication rule, we talked about when the AND happened, right? The event A and the event B happened. Now we talk about when the event A or the event B happened. So the probability of A or B is going to be the probability of A plus the probability of B minus the probability of the intersection. And we're going to go over some examples, and you will see that it's very simple. All this is doing is taking into account that you might be counting twice, pun not intended. So you want to be sure that you're not counting twice that overlap, so you subtract it. Do a couple examples and I'll make that clear. We just wanted the language of mutually exclusive, because if the events A and B are mutually exclusive, then this part is a 0. There's nobody there, right? A and B, there's nobody in their overlap, so that part disappears, and it makes this a lot easier. Just the add the sum of the probability of A and the probability of B. So there's ways to get confused. In the last videos, we talk about the probability of A and B. That's when you multiply the probabilities of A and the probability of B if they are independent. And here we're doing the probability of A or B, right? Which is, in this case, the addition of the probabilities if they're mutually exclusive. If they're not, you have to correct by subtracting this term once. Okay, let's do an example, see if you can figure out everything. I'm going again to my dice examples, and we're doing it over and over again. So you roll a pair of dice and you add the results. So let me get my grid here. Okay, so here's my grid. Find the probability of E or F. So E is the event you got an 8 when you roll a pair of dice. So the 8 I could have gotten with the 6 and the 2. Oops. The 6 and the 2, so that one, or the 5 and the 3, or the double 4, or the 3 and the 5, or the 2 and the 6. So it's that line right there. So the probability of that one of the die is a 3. So this one is a little bit tricky because I'm going to do this one with circles. So one of them is a 3, would include all this row in all this column. Right. So this is not strong enough. Let me see if that's good enough. Okay. So it's a little bit, when I use an example, I always think that this is not the best first example to do, but it's a good one to work it through, I guess. Here, what I'm going to do is say, I'm going to try to find what's the probability that an E or F happened. So E or F is basically anything that I marked there, right? And you can count them. How many little squares are occupied by either being painted in this blue greenish color or has a pink X on it. So I have 5 across, right, in diagonal, so 5 X's. But now on the blue, I already did that before. There's really 11, right? There's 6 3s across and 6 3s down, but you're double counting this middle one. So there's really just 11 of them. So, and then you still have to do the other ones. You're counting double these ones, right? So I'm doing it in my head. I'm going to do it carefully in a minute, but that's 11 plus 5 minus 2, right? Or 12 plus 5 minus 1 minus 2. So there's 11 plus 5, 16 minus 2. I think there's 14. And you can just count them directly, right? You can do it carefully here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 over 36. So I counted them directly from the picture, and I think there's 14 over 36. Now let me use a formula. It says the probability of E or F is going to be the probability of E plus the probability of F minus the probability of E and F. So what's the probability of E? E is an 8, getting an 8. So that's the one that was 5 over 36. What's the probability of F? That's where one of the die is a 3, so that's the 11 over 36. And the probability of E and F, that's these two, right? Those are the two that are either E and F, where they're both, the sum is an 8, and one of them is a 3. So it's that one and that one. So there are 2 of them, so minus 2. So that's what I did, and I got the 14 over 36. Okay, so they match if you just count them from the grid or if you use a formula. In this case, it was as complicated to do one or the other. This is the same. Oh, I wrote it here. Now, this is another example where I think it's a good one, but it's a little bit different. So now I think I have probably my grid pasted. Yes. So now, again, A is the event to obtain an 8. So I know what those are. Those are these diagonals, 6 and 2, 5 and 3, double 4, 3, 5, and 2, 6. But now, B is the event to obtaining an even number. And think about that for a minute. How many ways can I get an even number? It's not that hard to see that half of the sums are even, half of them are odd, right? It's going to be 18 out of 36. No, but of course, it's figure it out. So how I'm going to see it? I'm going to see it like this. When you add, I'm going to try to put these dots, but they're too big. Let me see. Maybe I can do this a little bit thinner. There you go. So these dots are going to make the doubles. Oh, let me erase that. Sorry. So the first one is a double 1. This is a 3, 1. This is the 5, 1. Right? Those are the ones that I get evens. Correct? Because the double 1 is 2. The 3 and the 1 is a 4. 5 and 1 is 6. The ones that I didn't do in that row are odds. In my next row, in the 2s, it goes like a checkerboard. It's the 2 and the 2, the 2 and the 4, and the 2 and the 6. Right. Now it's going to be like this. So it's not hard to see that. It's exactly like a chessboard or a checkerboard. They alternate. So those dots are the ones that have an even number. Now, if I use the formula that I had here, that I say, well, the probability of A or B is a probability of A plus the probability of B minus the probability of A intersection B or and B, right? It shouldn't look like a U. Just look like a, sorry, like that. So what's the probability that you get an 8? We already said that. It's 5 over 36. What's the probability that you get an even number? It's the dots, so it's 18 of 36. And then subtract the ones where you get both pink check mark and a red dot. So there were an 8 and an even number. So this is all 5 of them. Right? So really these are canceling. And you get the 18 over 36, so it's 1/2. Now, this is a weird example. I still think it's a good one. It's a weird one, but a good one to show what's happening here in terms of the sets in this Venn diagram. If you think about it, one set is inside the other one, right? So these are the even, but these are the inside when you get an 8. Right, because if you get an 8, it is an even number. So when one of them or the other one happen, we'll just consider the big one, right? You can just stay with the big 1/2. So we could have done it, but I wanted to show with the numbers how it's working out. I'm gonna do another short video after this.